Hi there, welcome to this video on the introduction of rheology. My name is Michael Deng and I'm currently a PhD candidate at the Shoichet Lab at the University of Toronto. My project focuses on the development of a long-acting drug delivery hydrogel for the treatment of chronic glaucoma. In this video, we'll be discussing the basic concepts of rheology and its importance in various industries. So, what is rheology? Simply put, rheology is the study of the flow and deformation of materials under applied stress. It is a branch of physics that deals with the behavior of complex fluids, including liquids, semi-solids, and soft solids. Rheology plays a crucial role in many industries, including food, cosmetic, pharmaceuticals, and plastics. In each of these industries, understanding the flow properties of materials is essential for developing and improving products. So one of the key concepts in rheology is viscosity. Viscosity is the measure of fluid's resistance to flow. It is a property that depends on the internal friction of the fluid and is typically measured in unit of Pascal-second or centipoise. High viscosity fluids such as honey or molasses flow slowly, while low viscosity fluids such as water or oil flow more easily. Another important concept in rheology is elasticity. Elasticity is the measure of material ability to deform and then return to its original shape. It is a property that is important in understanding the behavior of solids and semi-solids, such as rubber or gels. Finally, viscoelasticity is a property of materials that exhibits both viscous, liquid-like, or elastic, solid-like behavior under deformation. Viscoelastic materials are able to store and release energy over time, meaning that they can deform under the application of stress or strain and then gradually recover their original shape when the stress is removed. So, how can we measure these rheological properties? To measure rheological properties, various instruments are used, including rotational rheometers, capillary rheometers, and extensional rheometers. These instruments apply a controlled shear stress or strain to a sample and measure the resulting deformation or flow. Rotational rheometers measure the response of a sample to oscillatory shear or deformation. This type of rheometer can be used to measure the viscoelastic properties of materials such as gels, emulsions, or paste. Extensional rheometers are a type of rheometer that measure the extensional properties of materials. Unlike most rheometers that measure the deformation of flow behavior of materials under the shear or torsion, extensional rheometers apply a tensile stress to a sample in order to measure its extensional behavior. Capillary rheometers are a type of rheometer that are commonly used to measure the flow behavior of viscous materials such as polymer. The basic principle of operation involves forcing a sample of the material through a small diameter capillary tube and the control pressure and temperature conditions and measuring the resulting flow rate. Here I'm providing a brief tutorial of how to use a rotational rheometer. The first step is to set up the rotational rheometer according to the manufacturer instruction. This typically involves installing the necessary measuring geometries and ensuring that the geometry and the instrument are properly cleaned. Next, it is important to ensure that the instrument and the geometry are properly calibrated. To do that, you will need to open the software from Trios. Then you will need to click on the calibration button before clicking on the instrument button so that you can finally calibrate the instrument. The calibration of that instrument will take usually around 30 seconds. You will need to calibrate the geometry itself. To do that, you will need to go on the geometry section and calibrate three different types of calibration: the inertia, the friction, or the temperature. The temperature is only necessary for temperature ramps or temperature sweeps type of experiments. Following calibration, you'll need to name the test appropriately and design the procedure. To do that, you'll need to first input your sample name, input the operator name, and also put the nodes that will correspond to all the different parameters and also sample nature of your experiment. Next, you will need to also find the appropriate path in order to make sure that your test will be saved and your result will be saved in the appropriate folder. And also you will then design the procedure by inputting different type of parameters. You can do frequency sweeps, you can do strain sweeps, you can also do temperature ramps. This is really going to be depending on what type of data you would not need to get out of that. So now you're ready to load your sample. So first of all, you will need to perform a zero gap, which allows the geometry to zero and also to understand where would be the base of the instrument. After that, the program will ask you if you would like to go to the loading gap, and you'll need to press yes, and it will be raising the geometry so that you can load your sample. Here this is just an example of a paste that we're putting into the instrument, and after the loading you can press on the trim gap, which allows you to trim the excess product of that. Now you're ready to measure the viscoelastic properties of your gel. Here's an example of a type of experiment that you might conduct during your research. This is a time series experiment that analyzes the gelation time of a hydrogel. In this graph, you can see two different types of parameters being shown: the storage modulus, the G prime, and the loss modulus, the G double prime. The storage modulus, also known as the elastic modulus or Young's modulus, represents the ability of a material to store energy when deformed or release it when the stress is removed. It is a measure of the material's elastic behavior and reflects the amount of stress needed to deform the material. So the storage modulus is a measure of the solid-like behavior of a material and is often associated with its stiffness. On the other hand, the loss modulus, also known as viscous modulus or damping modulus, represent the ability of a material to dissipate energy as heat when it is deformed. It is a measure of the material's viscous behavior and reflects the amount of energy that is lost when the material is deformed. The loss modulus is a measure of the liquid-like behavior, this time of a material, and is often associated with its ability to flow. The goal of this experiment is to analyze when is the material becomes a gel. To do so, you simply need to analyze the ratio between the loss modulus and the storage modulus. In summary, if the loss modulus is higher than the storage modulus, the material behaves like a liquid. On the other hand, if the storage modulus is higher than the loss modulus, the material behaves more like a solid. In this case, we can see that the crossover point happens at around 25 minutes, which indicates that the material starts becoming like a gel-like type of material after 25 minutes. Thank you for watching this video. I hope that this will give you a little bit of an understanding of the rheology and how to use a rheometer. If you have any question, do not hesitate to contact me through my LinkedIn.